Most of the world's fertilizer is produced in large manufacturing plants, which require huge amounts of energy to generate the high temperatures and pressures needed to combine nitrogen and hydrogen into ammonia. MIT chemical engineers are working to develop a smaller scale alternative which they envision could be used to locally produce fertilizer for farmers in remote rural areas such as sub-Saharan Africa. Fertilizer is often hard to obtain in such areas because of the cost of transporting it from large manufacturing facilities. In a step toward that kind of small scale production, the research team has devised a way to combine hydrogen and nitrogen using electric current to generate a lithium catalyst where the reaction takes place. In the future, this research will provide a device that can breathe in air, take in water, have a solar panel hooked up to it, and be able to produce ammonia. This could be used by a farmer or a small community of farmers. For more than 100 years, fertilizer has been manufactured using the Haber-Bosch process, which combines atmospheric nitrogen with hydrogen gas to form ammonia. The hydrogen gas used for this process is usually obtained from methane derived from natural gas or other fossil fuels. Nitrogen is very unreactive, so high temperature, that is 500 degrees Celsius, and high pressure, that is 200 atmospheres, are required to make it react with hydrogen to form ammonia. Using this process, manufacturing plants can produce thousands of tons of ammonia per day, but they are expensive to run and they emit a great deal of carbon dioxide. Among all chemicals produced in large volume, ammonia is the largest contributor to greenhouse gas emissions. The MIT team set out to develop an alternative manufacturing method that could reduce those emissions with the added benefit of decentralized production. In many parts of the world, there is little infrastructure for distributing fertilizer, making it expensive to obtain fertilizer in those regions. While the Haber-Bosch process uses extreme heat and pressure to force nitrogen and hydrogen to react, the MIT team decided to try using electricity to achieve the same effect. Previous research has shown that applying electrical voltage can shift the equilibrium of the reaction so that it favors the formation of ammonia. However, it has been difficult to do this in an inexpensive and sustainable way. Most previous efforts to perform this reaction under normal temperatures and pressures have used a lithium catalyst to break the strong triple bond found in nitrogen gas molecules. The resulting product, lithium nitride, can then react with hydrogen atoms from an organic solvent to produce ammonia. However, the solvent typically used, tetrahydrofuran or THF, is expensive and is consumed by the reaction, so it needs to be continually replaced. The MIT team came up with a way to use hydrogen gas instead of THF as the source of hydrogen atoms. They designed a mesh-like electrode that allows nitrogen gas to diffuse through it and interact with hydrogen, which is dissolved in ethanol at the electrode surface. This stainless steel mesh structure is coated with a lithium catalyst produced by plating out lithium ions from solution. Nitrogen gas diffuses throughout the mesh and is converted to ammonia through a series of reaction steps mediated by lithium. This setup allows hydrogen and nitrogen to react at relatively high rates, despite the fact that they are usually not very soluble in any liquids, which makes it more challenging to react them at high rates. This stainless steel cloth is a way of very effectively conducting nitrogen gas with the catalyst, while also having the electrical and ionic connections that are needed. In most of their ammonia producing experiments, the researchers used nitrogen and hydrogen gases flowing in from a gas cylinder. However, they also showed that they could use water as a source of hydrogen by first electrolyzing the water and then flowing that hydrogen into their electrochemical reactor. The overall system is small enough to sit on a lab bench top, but it could be scaled up to produce larger quantities of ammonia by connecting many modules together. Another key challenge will be to improve the energy efficiency of the reaction, which now is only about 2% compared to 50 to 80% for the Haber-Bosch reaction. In addition to serving as a production method for small batches of fertilizer, this approach could also lend itself to energy storage. This idea, which is now being pursued by some scientists, calls for using electricity produced by wind or solar energy to power ammonia generation. The ammonia could then serve as a liquid fuel that would be relatively easy to store and transport.